So therefore, let us take this example. I am going to look at a 7,3 Hamming code. Okay. So what does this mean? It means that I can send only 4 bits of information. Okay. So let us say that I have 4 bits of information D0 to D3. Okay. And remember that I am going to now store this as 7 bits of information. Now I can do multiple things with this, right? I can just take D0 to D3 and then add the 3 parity bits P0 to P2, right? And just send it in this particular order, right? In the sense I have just taken 4 bits, appended 3 more bits and sent it. Or instead of this, I could choose to interleave the parity bits in a very clever way. Okay, and we'll see what that clever way is, right? So what I'm going to do now is I'm going to assume that I have what 7 bits of information, right? So I have bit position 7, 6, 5, 4, 3, 2 and 1. Okay, what I'm going to do here is I'm going to put my parity bit P0 here, okay, and P1 here. Then what I'll do, I will take D0 and put it here, right, and P2 here, D1, D2, D3. So instead of just appending blindly like that, I am actually interleaving these parity bits in a certain way. We'll see what the advantage of that is. Okay. Now, instead of actually, interleaving it like this, in order to keep the notation, I will just arbitrarily rename this as P1, P2, D3, P4, D5, D6 and D7. So instead of my data being D0 to D3, I am saying it is D3, D5, D6, D7. It's just a naming convention because I am just assigning the bit position to that index of the data or the parity. So it's very easy for us to see. So if you see the index on, going from right to left on parity or data, it will just be 1 to 7, right? Now what I'm going to do is I'll see how I can calculate these parity bits, right? I have 3 parity bits which are P1, P2 and P4. Okay, and I want to see how I can calculate this in order to correct 1 bit of error. So let us go back and see the binary representation of this. Okay, let's see 0, 0, 1. Remember, if the parity on the received syndrome happen to be 0, 0, 0, then there is no error. So I am not worried about that state. So let us look at bit positions 1 to 7. Okay, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, sorry, 1, 0, 1, 1, 1, 0 and 1, 1, 1, right? Now, all you have to do is look at, so this is 2 power 0, 2 power 1, 2 power 2. Okay, that's how the binary addition happens. So you look at, and this is, representative of P1 because 2 power 0 is 1. This is representative of P2 and this is P4 because 2 power 2 is 4. Okay. So if you look at the bits, that is where 2 power 0 happens to be 1, right? The digits, right? That happens to be in these things, right? So what is this? So this is index number 1, 2, 3, 4, 5, 6, 7. So therefore, I'll say my P1, okay, maybe I'll color code this. P1 is going to be D3 XORed with D5 XORed with D7. D3 XORed with D5 XORed with D7. Okay. Now, I am going to look at P2. Now, I have to see for what numbers, right, does the second bit happen to be 1. So, that happens for D3, D6, D7. So, I will say this is D3 XOR D6 XOR D7, right. And finally, I will say my P4, right, that is going to be D5, D6 and D7, okay. So, that is basically D5 XOR D6 XOR D7. So, what you do is you take the 4 bits of information and then perform these XORs and send 7 bits of information like this in this particular manner across the channel, and then we will see what happens, right. So, maybe what we will do is we will quickly work out one example, okay, for a specific case when, so let me take this here. Okay, and let us say, so what are my data bits? I am trying to send data D, which is what? D7, D6, D5 and D3. These are the 4 bits of data that I am trying to send across. Okay. So, what I will do is, if I want, let us say I want to send 0, 1, 1, 0. Okay. So, if this were the case, then what I have to do is, now I have to calculate P0, P2 and P4 like this. So, what is P0? So, P0, P1, I am sorry, is D3 XOR D5 XOR D7. So, it is going to be, so between D3, D5 and D3, D5 and D7, you have only one and therefore, you will have the XOR basically being a 1, right. Now, on the other hand, P2 is D3, D6 and D7, which again is going to be a 1 for you. And finally, P4 is going to be D5, D6, D7. So, you have even number of 1s and therefore, you will get a 0. Okay. So, therefore, what you are going to send eventually across the channel is that 7 bits of information, which is D7, D6, D5, P4, D3, P2 and P1, right. So, I will be sending the information in the following manner: 0, 1, 1, then I put P4, 0, maybe I will color code again, 0, then I come back to D3, right, and then P2 is 1 and P1 is also a 1. So, these 7 bits of information get sent across the channel, okay, and noise is going to corrupt at most 1 bit in them, okay. So, what we are now going to do is, of course, like I told you, we are going to send dn minus 1 all the way down to, or I will just call it dn to d1, right. This information, n bits of information, and of course, the parity bits are interleaved here, okay. When I say d1 to dn to d1, it is just n bits of information, or maybe I will just call it n bits of information, n minus 1 all the way to 1 like this, okay. I am going to send it across this channel and I am going to receive this now as some or maybe I will just use the exact example here. D7, D6, D5, D3, P4, P2, P1, right? And what I will end up receiving it as on the other end, right? Or what you end up reading it as from the memory is going to be D7 hat, D6 hat, D5 hat, D3 hat, and then I will receive it as P4 hat, P2 hat, and finally P1 hat. Okay. So what I can do now is I have received this, 7 plus 7 bits of information, 4 plus 3 as some other, bit pattern. Okay. But I can now calculate my parity of this P4, P2, P1 again based on what has been received, right? So P1 hat, P2 hat, P4 hat is my received parity based on what was transmitted and the parity that was calculated at the transmission side, right? On the receiving side, I can recalculate this parity and compare against these parity bits that were sent from the transmitter side, and that is going to give me the information of whether there is an error and exactly where that error is. So let us see what we are going to do. We are now going to calculate my parity bits again. Okay, I am going to calculate. So remember, so what I did, this is what was calculated at the transmitter, right? Now on the receiving side, I am going to do exactly the same calculation again. Okay. So what is this? So let me call this P1 dagger. Okay. That is the parity that is based on the received bit stream. Okay. And what is this going to be? It is going to be D3 hat XOR D5 hat XOR D7 hat. Likewise, my P2 dagger, right, is going to be D3 hat XOR D6 hat XOR D7 hat, right? And my P4 dagger is in purple. P4 dagger is going to be D5 hat XOR D6 hat XOR D7 hat. So remember that we are talking about only 1 bit error here, which means most of the D hat values are exactly the same as the D values, right? It's only 1 or 2 values that are actually going to be different. So intuitively, how is this going to help us, right? So if you look at this P1, P2 and P4, right? If you look at these values, there is D3, D5, D7. So let us assume for now that D5 happened to be in error. Now if D5 is in error, instead of calculating the this thing, right, instead of the parity value will change for P1 and P4, right? So P1 is wrong, P4 is wrong because D5 has now been inverted, right? But P2 will remain unaltered. So this unique combination is actually going to tell you that if P1 is in error, P2 is not in error and P4 is in error, then D5 happens to be the one that is at fault. Okay. So let us see the example again here. We had actually sent, what is the bit pattern that we sent? Let's also take this now to the other page. right? This is what I have, and I am saying the bits that were transmitted, only D5 happens to be in error. That means D7 is correct. So if you look at the hat versions, D7 hat, D6 hat, D5 hat, P4 hat, right? You would have received it as 0, 1, and let me use red to introduce the error. D5 alone is received as a 0 instead of a 1, right? And the remaining bits are basically exactly the same that were transmitted, right? 0, 1 and 1. Okay. So what we are going to do now is, we are going to calculate these values for us, right? This is going to be D3 hat XORed with D5 hat and D7 hat, right? So what is D3 hat? It is going to be 0. D5 hat is going to be 0, and D7 also is 0, and therefore the XOR of this will end up being 0. Okay. Now, what is this value? P2 hat is just D3 hat XOR D6 hat XOR D7. Now that is going to remain unchanged because there is no error in any of these bits, right? And finally, if you look at P4 hat, it is going to be D5, D6 and D7, and of course, what was 0 will now become a 1. Okay. So now what we are going to say is, I am going to evaluate my syndrome in the following way. My syndrome is SK is just going to be my PK hat XORed with PK hat is the received received parity, right? And I am going to XOR this with the newly calculated parity, right? So if I do this, then I'll get the syndrome. Okay. So in this case, I have 3 bits, okay, and therefore I have S1, which is going to be my P1 hat XORed with P1 dagger, right? So what was sent as 1 came out as 0, and therefore that XOR is going to give me 1 here, right? Now S2 on the other hand is going to be P2 hat XOR P2 dagger. And what is this going to be? It is basically going to be the XOR of these two, 1 and 1, and therefore you get 0 as the answer there, right? And finally S4, it is P4 hat XORed with P4 dagger, right? And therefore that is going to be XOR of 0 with 1, and therefore I get 1. Now, how do I find out which bit is an error? All I have to do is order this as as S4, S2, S1, and look at the binary representation of that. That happens to be 1. Again, I'll put it in color code: 1, 0, and 1. And magically, what you see is 101 happens to be the binary representation of 5. And it is hardly surprising that the 5th bit is an error, and therefore all I have to do to get the corrected bit out of this is to flip D5 and get the correct answer out of this. So it is amazing how, we have, that's why the position of these bits is very, very important. Okay, and it is very, very critical for us to place the bits in this order and send it, so that the syndrome actually eventually tells us the exact bit position. Otherwise, the syndrome will, give us a certain mapping. Each syndrome code will correctly map to one of the bits being, in error. But that mapping can be quite complicated. So from an implementation perspective, this is a very, very nice thing, as you will see next, because I'll show you what is the circuit that is actually needed in order to fix all of these errors, right? So, so maybe, just to convince ourselves that this whole thing is correct, right? You can also, I would urge you to please go ahead and try to solve this for various other examples. Okay. Now let us actually look at these things a little bit. So if the data, one of the data bits happens to be in error, right? That is D5 became D5 bar, right? Then what would happen is the received parity, right? That the P daggers would, two of them would sort of be different from what was transmitted, right? On the other hand, if it was one of the parity bits that were in error, right? For example, so let us do this, maybe we'll do the same example now, but instead of, instead of D5 being in error, right? We will just try the example of one of the parity bits itself being in error here, okay? So I am going to copy this example, right? Right, now what I am going to say is, instead of this case, I am going to assume that exactly D5 was not in error. Let us say it's my P2 that happened to be in error, right? This guy happens to be the error. P2 hat happens to be in error, right? Then this is a very interesting case, because based on what was received, when you calculate the parity values, right? The parity values when you recalculate, because what happens is P1 dagger is D3 hat XOR D5 hat XOR D7 hat, but we know that all those bits D3, D5, D6, D7 were received correctly. That means they are all going to match the original parity that was supposed to have been transmitted. Okay, so this will be 1, this will be 0, and this will be this will also be 1, and this will be 0. Okay, but what you know is that P2 hat happens to be in error. So when you calculate the syndrome now, right, S1 will be P1 hat XOR P1 dagger, right? And that happens to be 1 XOR 1, and therefore that is going to be 0. S2 is going to be P2 hat XOR P2 dagger, right? And that is what is in error now. So you will get 1 here, and S4 will be P2 will be P4 hat XOR P4 dagger, and therefore that will also be 0. So when I now put this syndrome in this order, S4, S2, S1, the binary representation, and I look at it, it would be 0, 1, 0, and this basically says bit position 2 is in error here. That's exactly what we wanted. So basically the point is, if the data bits happen to be in error, 2 of the parity calculations will differ on the received side compared to what was transmitted. But if the parity bit happens to be in error, in this specific arrangement and position that we have chosen, then only that parity bit will go wrong. That means the data bit, there is nothing wrong. Okay, so that's how we basically use this whole example. We use this representation to specifically identify which bit is an error. Okay, so let us now look at the implementation, right? Because what we have done till now is, on the transmitted side, what do I need? I just need a bunch of XOR gates. I just need a bunch of XOR gates, because all I have to do on the transmitter side is to evaluate these parity bits as shown here, right? D3 XOR, let me just maybe take that. Right, I will just remove these values. So if you look at this, on the transmitter side, it's a bunch of XOR gates. On the receiver side again, if you look at it, this is again a bunch of XOR gates. Alright, and remember, our syndrome, right, was also calculated just with very simple XOR gates, and therefore really there is nothing extraordinary that is required. Just bunch of XOR gates till now we have been able to solve. So on the receiver side, even the syndrome, right, yeah, right. So if you look at this, even the syndrome calculation is just bunch of XOR gates, some 3 input, 2 input XOR. If you go to higher bits, you need multi-input XOR gates, really, that's all. But now, how do I actually implement the error correction? Because what we are now saying is, I take S4, S2, S1, that binary representation is what is going to tell me which bit is in error, right? And how do I fix this, right? So what we are going to do is, and this is where the idea of arranging it in this particular sequence is going to help, because all I need to do now is to take this S4, S2 and S1, the calculated syndrome, and give it to a decoder, right? A 3:8 decoder, of course 0. So, and what does syndrome value 0, 0, 0 mean? There is no error. That means all the received parities have matched what was transmitted, and therefore there is no error in transmission. So any other bit is all that I have to worry about. So all I have to do now on the receiver side is to give this 3:8 decoder. Okay, I give S, S4, S2, S1, right? And I am going to get 8 outputs from this. 4, 5, 6, 7, 8. 0 is no error. 1 to 7 is going to tell me exactly which bit position is in error. Okay, so if for example bit position 1 was an error, that is a parity bit is an error, that means that this guy will go high, everything else will be a 0. Okay, now in order to generate, in order to fix the error, what do I have to do? All I have to do is to take this received bits, the D hats or the P hats, and simply XOR it with this value. For example, this is another XOR. This is P1, and I will receive this bit. So for this is going to be my P2, right? And this is my P1 hat, P2 hat, and I will get the actual value out. For example, D7 is my received value, and I give D7 hat here. So let us say that syndrome value was 0, 1, 0. It means the fifth output of this decoder, 5, 6, 7, this will go high, and this is going to get XORed with D phi hat. And that's what we did. All you had to do was invert D phi hat, the received bit, and you get the actual transmitted bit on this side without any error, right? So you just do this implementation, right? And maybe now you don't care for the parity, right? So all you have to do is literally you have to implement this for the 4 data bits that you sent from the transmitter side and give the output here. So instead of doing all of this, what I would do is instead, right, because now I don't care for the parity bit error, I will take 2, 3, right? So 1, 2. So this is my D3. This is my D3 hat. And this will be exactly equal to D3 now. Okay. D5 hat. D6 hat, and this will be equal to D6. D7 hat, and this will be equal to D7. So you started off with wanting to send D3, D5, D6, D7, those 4 bits across the channel or reading it from the memory without any error, and now you have been able to retrieve exactly D3, D5, D6, D7 on the other side, provided only 1 bit happens to be in error, and that bit could be any of these bits. Okay. So next what we can do is you can look at a few more examples of the 7,3 code, and maybe we'll also look at the next. Suppose I have 4 bits of parity, right? Then how many bits of information can I send? How do I extend the same logic to a higher number of bits as well? Okay, thank you.